In this video we're going to derive the differential equation that describes the motion of a simple pendulum using the Euler-Lagrange method. So if we draw out a simple pendulum, the length of the pendulum is L, there's a little bob at the end of mass M, and if we draw down the perpendicular, the pendulum will make an angle theta with this perpendicular. So the pendulum is going to swing in a circle. Now, if we use the conservation of energy, then what we can say is that the change in the kinetic energy is going to equal the change in the potential energy. So what's going to happen is the pendulum is going to start up at some position here with a maximum potential energy, and the kinetic energy will be zero because it will be sitting still at that point, and then when we release it, the potential energy decreases and the kinetic energy will increase until it hits this point here, at which point the kinetic energy will be a maximum and the potential energy will be a minimum. So if we look at these two separately, so we can look at the change in the potential energy. Now, the change in potential energy is going to be mass times the gravity times the height. Now, it's going to be the change in height, delta H. Now the change in height there is the difference in height between, say, this point here and that point there, which is a release point. So if we could just draw a little line across here. Now, we know this length here from that point to that point, just continue the circle around that point, the length is the same length as the pendulum, so that's just the length of the pendulum. So that delta H is going to equal, well, it's the length of that pendulum, L, minus this length here. Now that length there is just going to be the L cos theta. L cos theta. So delta H, we take out the common factor of L, it's going to be L1 minus cos of theta. So we can say then that the change in the potential energy of the system is going to be equal to mass times gravity times L1 minus cos of theta. Okay, so we can call that equation number 1. Now, the kinetic energy of the system, change in energy kinetic, is going to equal, well, it'll be a half m times the velocity squared, which is the initial starting velocity, vi, and the final velocity at that point there, which is going to be vf. Now, if we say at t equals 0, the velocity, the initial velocity equals 0, so we're holding the pendulum at that point there. At that point, time is 0 and the velocity of the pendulum is 0, then we can see then that vi is equal to 0. So therefore we can say that change in kinetic energy is going to equal a half m times the v final squared. Now I'll just drop the f, okay, and we'll just leave it with the v squared. So it's a half m v squared is the change in kinetic energy. But we want to write this in v here, instead of terms of a linear velocity, we want to write it in terms of an angular velocity. So if we note that this little part of the curve here, we call that little segment of curve S. So that curve there, it's an arc that's subtended by this angle theta. Okay, so now if theta is in radians, then we can say that that little arc S will be equal L times theta. Now, if you're unsure about where that comes from, I've got a video in the snippet section that describes all about angular displacement, angular velocity, and angular acceleration. So have a little look at that video in the snippet section if you're unsure. Okay, so we can then say that the angular velocity is going to be the rate of change of angular position with respect to time. So I'll just write it in the dot notation. So s dot, so that just represents ds by dt. When we differentiate the other side, well, the length of the pendulum is fixed, there's no variation. The only thing that's got variation of time is that angle theta, so that's going to be theta dot. Okay, so it means that we can then put L theta dot in for the value of v, so we're left with energy kinetic is going to equal a half m Now it's going to be v squared, which in this case here is going to be this L squared theta dot squared. Okay, so that's really equation number 2. So now we're going to equate both of these equations. So we're saying that the kinetic energy, a half m L squared theta dot squared, is going to equal the potential energy, which is going to equal mg L 1 minus cos of theta. Now what we're interested in here is the angular velocity, theta dot. Okay, so if we rewrite this in terms of theta dot, so theta dot is going to equal our value. In fact, we don't even need to get to that point there. We can just leave these two equations as they are at the moment, so there's no need to get into that detail. Yeah, I'll just leave that as is. So we've derived the two things that we're looking for. We're looking for the kinetic energy and the potential energy. So now we're going to use the Lagrange method. So we can say then that the Lagrangian is going to equal the kinetic energy minus the potential energy. Okay, so in this instance here it's going to equal a half m L squared theta dot squared minus the potential, which is mgl 1 minus cos of theta. Okay, so that's the Lagrangian that we're looking for. Then we can use the Euler-Lagrange in order to find the differential equation that describes the motion. So we can say from the Euler-Lagrange that partial L by partial theta is going to equal d by dt partial L upon partial theta dot. Okay, so we'll split this up and we'll look at partial L by partial theta. So partial L by partial theta, so there's no theta term there, there's only a theta derivative. We're only interested in the theta term, so that's the theta term there. Okay, so that's the second term there. So when I differentiate that with respect to theta, I'll get partial L upon partial theta will equal, well, it's still going to be our, when I differentiate cos, I get minus sine. Okay, so the minus will cancel that to give a plus, but we're still left with a minus there. Okay, so we'll end up with a minus. Now the m and g and l just act as constants, and the differentiation will be sine of theta. Okay, now they're also interested in partial L by partial theta dot. There's a dot there. Okay, so we're differentiating this thing up here with respect to this theta dot. Okay, so when we differentiate that there, we're just going to be left with, well, the 2 is going to come down, so it's going to be 2 times a half ml squared theta dot times the theta dot. Okay, so you're just going to end up with your value here, which will be m and L squared and your value of your theta dot. Okay, because the 2 comes down and cancels with that 2 there, you're just left with your m and your L squared, and that will just be left with your value of theta dot. Okay, so that's the first part of that. Now the second part of that, I've got to then differentiate that again with respect to time. So d by dt of this thing here, m L squared theta dot. Now the only thing that has got a function of time here is that theta. Okay, so you're simply going to be left with m L squared theta double dot. Okay, so now we equate both of those. We're left with our m L squared theta double dot is going to equal this thing here, which is a mg L sine of theta. Okay, so it means that we can then rewrite that as theta double dot equals, the m's cancel out and the L squared comes down, one of the L's cancels on the top line, one cancels on the bottom, so you've got your value, if there's a minus there as well, you get your value there of minus G upon L sine of theta. So you get the final differential equation for that describes the motion of a pendulum will equal, take the minus across, will become G upon L sine of theta equals 0. Okay, so that there is a derivation of the differential equation that describes the motion of a simple single pendulum. I've also got this derivation done using a standard form in the calculus of variations, and in the section on differential equations, and I've also got this same derivation which has been programmed into VPython, so you can see it physically moving, and a description of that program. Okay, so thank you for listening and goodbye.